All right, let's go ahead and get started. I want to welcome you to Unit 7, Chemical Reactions. We've been talking about various types of chemical reactions in this unit, but we want to focus now on nuclear chemistry. And as it turns out, nuclear chemistry is a very important topic because of the fact that it holds the promise nuclear power will probably be a very major factor in the way that we will power our futures. Certainly there will be other ways of obtaining power, like wind power, for example, or wave or tidal power that are going to be important. But nuclear chemistry and nuclear power are going to play vital roles, no doubt, in the way that we handle the coming energy demands. So let's start with the definition. Radioactivity. What do we mean by radioactivity? Well, it's a property of matter whereby an unstable nucleus, and that's key, unstable nucleus, spontaneously emits small particles and or energy in order to attain a more stable nuclear state. So when we have an atom, and that atom has a nucleus that is unstable. Remember that the universe is in the constant state of increasing disorder, what we call entropy. And everything in the universe is trying to get to a lower energy state, including these unstable nuclei. So when we have a radioactive particle, maybe it is a uranium atom, that uranium atom is going to do everything it can to get to a more stable configuration. That nucleus is going to do what it needs to do. And if that means spit out energy, it's going to do that. If that means releasing particles, it's going to do that. And so that's what we mean by radioactivity, and that's where we'll start. So what's the difference between a chemical reaction and a nuclear reaction? Well, let's sum it up. Chemical reactions are reactions in which bonds are broken and formed. All right, so we've talked extensively now about normal chemical reactions. What happens in a chemical reaction is that some bonds are broken, some bonds are formed, and going from or transitioning from reactants to products. A second characteristic of chemical reactions is that atoms are unchanged, but rearranged. We go back to Dalton for this idea that matter can't be created, can't be destroyed. But the atoms themselves don't change in any way. They're just rearranged in chemical reactions. Chemical reactions involve outer level electrons, valence electrons. So when we have ionic bonds or covalent bonds or metallic bonds, those are going to be formed by the involvement or through the involvement of only the outer shell electrons, called the valence electrons. Also, chemical reactions involve only small energy changes. So we're going to be talking later about something called enthalpy or delta H. And we'll learn that some reactions require energy and some reactions release energy. But it's a relatively small amount of energy involved when we're talking about chemical reactions. And finally, the rate of reactions is affected by temperature, pressure, concentration, and catalysts. All of those are going to affect the rate of the reaction. All right? All of those are going to affect the rate of the reaction. Now let's contrast that then with nuclear reactions. In nuclear reactions, nuclei emit particles and or energy. We've already said that. All right? Second, atoms are sometimes changed into other atoms. Now that's counter to what we've said before. What we've always been saying what we said from the beginning is that matter cannot be created and cannot be destroyed. But at the nuclear level, atoms can be changed into other atoms. Next, this involves protons, neutrons, and electrons, right? So when we're talking about nuclear reactions, we're not just talking about outer electrons. We're talking about protons, neutrons, and electrons. The energy changes are huge. They're so big that these types of energy changes can be used to do things like power a submarine. They can do things like provide an entire city with electricity. And they can be used for bad things too, like building bombs that can demolish many city blocks, okay? So huge energy changes involved in nuclear reactions. And next, the rate of reaction is not affected by temperature, pressure, concentration, or catalysts. None of those affect how fast nuclear reactions occur. So that's it. All right, so we've got conventional chemical reactions, and we've got now nuclear reactions. Now, there are a number of things which can fall out of a nucleus. So we've talked about how the nucleus can be unstable and how it releases things. And one of the things that can be released is something called a beta particle. Now, what is a beta particle? Well, we can think of a beta particle as an electron. Okay, so a beta particle is an electron. So if you hear the term, for example, beta emission, beta emission means that a particle, the equivalent of an electron, has fallen out of the nucleus, has come out or been ejected from the nucleus. Now, I know you're bright people and you're going to say, wait a minute. What do you mean an electron has been ejected from the nucleus? The electron was not present in the nucleus in the first place. How can you eject an electron from the nucleus when it wasn't there to begin with? Well, it's important that you understand that it's not an electron. It's the equivalent of electron, but it's a separate species, one that exists in the nucleus. Beta particles are written with the following symbols. You can either write it like this, with an E for electron. The -1 stands for the charge, and the 0 on top stands for the mass. For all intents and purposes, the mass is 0. Or you can simply write it like this. This is not a B. It's kind of like a cursive B, right? And you're going to need to get practice in writing these, by the way. So it's kind of like a cursive B, just like that. You just put a negative right there. And so that's a beta particle. So that's the first particle, first thing that can be released from the nucleus of the atom. And again, the -1 subscript indicates that the charge of the beta particle is -1. Electrons have -1 charges, okay? And the 0 superscript indicates the mass of the beta particle is, for all intents and purposes, just 0, all right? So that's a beta particle. The following reaction represents beta decay. I've said beta emission before. We can also say it beta decay. That means that the nucleus is going to release a beta particle. Notice that an electron, otherwise known as a beta particle, and I say an electron, I really shouldn't have said that because it's not an electron, but a particle like an electron, equivalent to an electron, otherwise known as a beta particle, is emitted and a new element is formed. Carbon becomes a nitrogen 14. Let's take a look at how this happens. So here we go. We've got carbon 14. This is an isotope of carbon that has 6 protons, as all carbon atoms do, and 14 protons and neutrons. That means it has how many neutrons, by the way? Well, the difference between these two, 14 minus 6 is 8, right? So 8 neutrons. And look what we have on this side, a beta particle. So the beta particle was ejected, but here's what you need to know. That the numbers on bottom and the numbers on bottom have to be equivalent on left and right. In any nuclear reaction, these numbers have to add up on the bottom and on the top. So on the bottom, what plus -1 is 6? 7, right? What 14 plus 0 is 14, so we put a 14 right there. But what's the element that has 7 protons? Look on your periodic table. What has 7 protons? Nitrogen. That means that carbon became nitrogen. Carbon became a new element, all right? That's something that's new to us. In chemistry to this point, we're on unit 7 now, we've never seen an element turn into another element, right? Turn into another element. Now, another type of particle which is sometimes emitted from the nucleus is known as a positron. So we've looked at beta particles. What about positrons? Its symbol is shown below. Notice the similarity to the beta particle. Positrons are just like electrons, or I should say positrons are just like beta particles in that they have 0 charge, right? But no, they have 0 mass. 0 mass. But look, the charge is +1. It's almost like an electron with a positive charge. Okay, folks, Nuclear chemistry just gets weird sometimes, and you just have to go with the flow, okay? It's like an electron with a positive charge, just accept it, all right? We've never even thought about things like that. We've already shown that electrons have negative charge, but now we've talked about a positron having it's like an electron with a positive charge. Weird things happen at the nuclear level, so we just kind of have to accept it, all right? So notice that the positron is kind of like an electron that has a charge that's positive. Now shown below is an example of positron emission. Remember, emission means like spit out. That's what emit means. Emission means like release. Shown below is an example of positron emission, in which oxygen becomes nitrogen. So we're seeing now elements become new elements. We've got oxygen. How do I know it's oxygen? Well, it has 8 protons, right? 15. How many neutrons are there in this isotope of oxygen? Well, the difference between 15 and 8 is what? 7. So 7 neutrons. Now, I've got this positron here, plus 1 right here, 0 right there. 1 plus 7 is what? 1 plus 7 is 8. So that means a 7 goes there. So what's the element that has 7 protons? Look on your periodic table. What's the element that has 7 protons? Nitrogen. All right, so this is nitrogen 15. So oxygen became nitrogen in this positron emission. All right, let's talk now about electron capture. All right, we've talked about electron emission or beta emission. I want to talk about electron capture now. What is it? This occurs when a nucleus is made more stable by incorporating an electron. So we're not going to spit out an electron this time. We're going to incorporate the electron. And again, you say, wait a minute. The electron shouldn't be in the nucleus. Well, it's not really an electron. It's like an electron. It's a beta particle that's supposed to be in the nucleus, okay? So get used to these ideas. They're weird, but you just have to accept them, okay? So here potassium incorporates an electron to become argon. Remember, the numbers on the bottom have to add up, right? The numbers on bottom have to add up. So here we have 19 minus 1 is 18. All right, 19 minus 1 is 18. 40 plus 0 is 40. So when you look at the 18th element on your periodic table, that's going to be argon. Electron capture, we call that. All right? In electron capture, an inner shell electron is incorporated into the nucleus of the atom. So it's not some valence electron way out far in the periphery. We're talking about inner shell electrons, close to the nucleus anyway. And they just get sucked into the nucleus. Now, an alpha particle is known as a helium nucleus. An alpha particle is a helium nucleus. All right? Its symbol is as follows. Now, we've got helium, 2 protons in the nucleus, 2 more neutrons in the nucleus, right? But this is a helium nucleus, and it's known as an alpha particle. An alpha particle. This is an alpha particle. Folks, go back in your memory and remember the gold foil experiment. Think about that experiment, the gold foil experiment. It's where something was shot at gold metal, a thin sheet of metal, and the particles deflected. What were those particles? They were alpha particles, all right? They were alpha particles, all right? All right. So here we go. It says the following equation shows the alpha decay of polonium. Notice polonium-210 becomes lead-206. Let's see how that's going to work. So here we go. We've got polonium-210. This is 84 here. Becoming, here's the helium nucleus here, right? Here's the helium nucleus here that's been ejected. Note that balancing nuclear reactions requires balancing atomic charges and atomic numbers. The numbers on the top of the arrow must add up, and the numbers below must add up. All right? Now, sometimes a nucleus does not emit matter, but emits energy in the form of what is known as gamma rays. The symbol for this type of radiation is this symbol right here. It's kind of like a cursive Y. Folks, we'll pick this up on the next one. I'll see you then. Thanks.